So welcome everyone. We've got a special session of Etro U today hosted by our own James from our VDC group. And he's going to be taking you through an introduction to what VDC is and what his group does on all of our projects. So James, you can have the floor.
Thank you very much, Karina, and thank you everyone for making the time today. That's very much appreciated. So welcome to VDC 101, or by another title, this is VDC at LOD 100. By the end of this session, that title will hopefully make sense to you. I want to give you the overview up front so that you know what to expect and to motivate some of the earlier slides that can seem a little abstract. And then we'll cover some of the tools, some of the jargon, and I hope that will make the technical aspects of what we do a little bit less intimidating. And then finally, we'll go through how to use those tools, how to set up your project to get the most value out of those processes that we have available. So first up, I'm going to give a brief personal introduction. I'm going to talk about perspective alignment. So I've framed myself here in two fonts. The Comic Sans version of me is that I'm from Salt Spring Island near Victoria. And when I'm not here at Etro, I like to be kayaking. I sing with the Grace Note Vancouver Choral Society. I really like doing puzzles, everything from Rubik's Cubes to Sudoku variants. Don't get me started, I'll talk your ear off. Sorry, Melinda. The other perspective here is in the Etro favorite Roboto Bold. I did my bachelor's degree in applied science at UBC in engineering physics, and I was working in search and rescue drone technology for a while. And then towards the end of my degree, I was back on the island for a while. I wanted to build this little shed that you're seeing in the image there. So I got some help from family and friends. We poured the foundation, framed it up with some stock surplus doors, windows, vents, and then I roofed and shingled it myself. And then I didn't get around to cutting back the exposed tar paper on the top there or putting in a proper doorknob before I took that picture. Which is part of the reason that I am an office guy, not a site guy. It's obviously far from perfectly executed, but I just found that process so satisfying that I pretty much immediately pivoted away from robotics and went towards construction to see how I could apply what I already knew in this world. So I'd been using design modeling technology at the time, mostly for drone fuselages. So I went and picked up some similar software, and that opened the door to BIM and BIM consulting. And then that put me in contact with Etro through Xenia. So I've been a VDC coordinator now for almost 3 years now at Etro. And it's not unusual for people in VDC to take unusual paths like this into the field because it is inherently multidisciplinary. And I hope that by the end of the session, you'll have a little bit more context for what it is that we do and why we do it. And let's start with that why. Again, this is a 3-part presentation. What are our objectives? What are our tools? How can we apply those tools to meet the objectives? This section, the why section, only has one slide in it. Here, I'll flip forward. One slide, section 2. Seriously, a third of the presentation is just that one slide, and that's because it is so fundamentally important. And this graph that you're seeing now is in almost every presentation about VDC that you'll ever go to. It's one of the first things that you'll see when you start talking about the subject. And it's extremely important to us. It's the same reason that Etro values pre-construction and estimating. And it's an illustration of the simple truth that the later you are in a project, the more expensive it is to make changes. In other words, the sooner you're aware of an issue, the cheaper and easier it is to solve it. This is true for individual activities, for project phases, and for the project as a whole. Typically, most changes can't be anticipated, so by the time they get to us, all we can do is mitigate the impact on budget and schedule as best we can. The graph is usually called the McLeamy curve, after Patrick McLeamy, longtime CEO of HOK, which I believe is now the 4th largest architecture firm, but when he first used it in 2001, they were already very influential. But in 2001, this graph was already 25 years old, so I prefer to attribute it to the original author of the graph, as far as I'm aware, which is Boyd Paulson. He created an identical one in 1976, and it's been published in construction management textbooks since at least 1991, with the correct attribution. So you might already know this under the McLeamy curve name, but I'll be referring to it as the Paulson curve. And I want to just give a quick example of the typical process and how this applies to that. So I want you to think about the costs associated with making a change over the course of commissioning, getting to the point of commissioning a single piece of equipment. So first of all, let's say it's a transformer or an air handling unit or something. So let's say the requirements are determined by the engineering consultant, and then there's a selection process of the unit that meets the requirements. You source a supplier, you place an order, you receive it, you deliver it to the location on site, and then there's installing, inspecting, commissioning, sign off, etc. And the later you are in that process, the more expensive it would be to make a design change in that. It means your lead time gets reset. It means you're paying restocking fees, you're recoordinating systems around the change. If it's already on site, you're double handling. Maybe you're taking down a ceiling that was already installed. I don't need to tell any of you that rework is expensive. That's not news to anyone here. But that's a case of a sort of a known unknown. Equipment selection and procurement is a known risk to budget and schedule, and that's why we have experts like Ben Brower here in-house with the experience to anticipate and to manage risks. So more importantly for us are the unknown unknowns. How can we identify problems so that we can solve them if we haven't encountered the circumstances that lead to them yet? So imagine you're just finishing a project, congratulations, you've just been awarded substantial completion. And then you wake up the next morning and Groundhog Day rules are in effect. You're back at the first day of pre-con. So if you had to build exactly the same project again from that point, how much time and money could you save compared to the first time, knowing everything that you know now? And that kind of familiarity and efficiency is the reason we want to shift our efforts earlier into the project, and the efforts of the consultants and the contractors as well. If there are going to be changes, we want everyone to know about them as soon as possible to avoid rework and sunk costs. For Etro in particular, because we tend to build unique specialty projects, we encounter lots of unique specialty project conditions. There aren't lots of opportunities to apply lessons learned, for example, on fossil storage systems or prefabricated sky bridges or fabric-based organically shaped concrete forming methods. So finding ways to identify these challenges farther in advance is all the more important when we don't have comparable lessons learned to compare to. So that's our main objective: shift effort earlier, solve problems sooner, and avoid the uphill battle trying to do it all during the project itself. So what tools do we have in order to achieve that goal? I'm going to start with some of the essential terminology so that you understand where I'm going with all of this. BIM, as a noun, refers to both the process of creating building information models and the models themselves. So information is the key word here. If data isn't integrated with the geometry, that's a 3D model, but it's not BIM. And then VDC is a broader term. It includes the production and the coordination of models, and then it also includes using those models to ask and answer questions. LOD and BXP I will return to in more detail later, but for now, if LOD just means level of development to you and you don't really know what that means, and similar for BXP, BIM execution plan, that's fine. We'll come back to it in a moment. So the crux of a VDC process, the sort of hub of a hub and spoke integrated model. In a traditional coordination and planning process, your raw materials are things like design documents, shop drawings, specifications, etc. But in a VDC process, BIM is the raw material, and the federated model is where all of the latest BIM, everyone's latest models, are overlaid into a single location. And this metaphor is maybe a bit out of date, but it's as if you had a light table that was so strong that you could lay all of your plans and all of your sections from every source on top of each other and have an overlay of everything all at once. And needless to say, if you did that with a real light table, it would be extremely overwhelming, hard to look at, hard to get any information out of that. But the reason that these tools are so powerful is that we get the ability to filter and process that information. So this is what we were looking at a moment ago, but just broken down a little bit. So that messy piece on the bottom left there is actually constituted of all of these models that come from all of these sources. And a question that I wish I got asked more often is, where did these models come from? Who's the author of this? This is the project according to who? So models can come from lots of different sources. That has a huge impact on how they can be used to help the project. Architects, consultants, contractors, fabricators, they all produce models. And then we use various processes to capture existing data about the site as well. So sometimes if there's a system that isn't being modeled, or more commonly isn't being updated, our team will step in to make sure the rest of the team can progress. It's not an ideal case though. The best case scenario is that the foremost expert on every system at any given time is the one responsible for that model. And typically to achieve this, that means authorship over some elements gets transferred through the project. For example, in the top right there is the fire protection model from the fire protection consultant, and then right below that is the installation model from the fire protection contractor. So once the design is complete and represented by the consultant, the contractor can take over and fine tune for installability. They can account for any offsets that they need to avoid other systems. They can optimize the arrangement of their fittings and do that kind of thing. So well-coordinated models are like different perspectives on the same story. And the process of coordination, what we're trying to do in its simplest form, is to develop and maintain a shared understanding of that story. And when two parties don't understand the same way, that's where you get issues. When geometry isn't understood the same way by two different groups, you get a clash. When responsibility isn't understood consistently, you get a scope gap. And lots of the work that we do as a GC is about bringing different parties together to get a shared understanding of the project. And the bigger and more complex the project is, the more information needs to be aligned. So being able to transmit and process these large data sets becomes more important. And making this data approachable and intuitive to navigate is more of an art than a science, but there are some things that you can do in general to make it easier to digest information this way. I'll show you a few of them in a quick little video presentation here. So this is a clip to show you what it's like to actually navigate this kind of data in 3D. We're flying under the slab here, and then we'll go up above and into the ceiling. There we are, and then we'll go down into this little commercial kitchen space. So there are some strategies in here that are being used to make sure that this is communicated in a way that you don't need to learn to interpret this. You know, people have to be taught to read drawings, but reading a model comes pretty intuitively for people. So the strategies that we're using here, one is I'm not showing all the information at once. This is just showing the latest trade models and the architectural base model. It's good practice to avoid duplicates in any 3D view unless you're explicitly comparing versions, unless your goal is to understand the difference between two views of the same system. The second one is we're using lots of section planes to limit the scope being viewed at any one time. And then the third one is to use a first-person perspective, which matches what you see in the real world more closely. And that last strategy is one of the main advantages of working in 3D, which is that it lets you use visual processing the way your brain has been practicing your whole life. Human brains have a bit of a home field advantage taking in information like this, and it may seem counterintuitive because some of these tools do have a learning curve. But once you're established there, it becomes 1,000 times easier to communicate it to the next person who is looking at it in a familiar lens. And it matches closely what they will see in the real world. So in addition to making use of your brain's existing ability to process spatial information, using model data has the advantage of automation. One of the major types of misaligned information is also luckily very easy to identify algorithmically, and that's geometric overlap. So this is a clash test. If you've heard one phrase about VDC and what we do, clash detection or clash testing might be that phrase. And a clash is simply two objects which are shown existing in the same location at the same time, which is contrary to possibility when it comes to install. So a typical process for identifying a clash is a workflow that is some variation of clash, sort, report, track, and repeat. So I'm going to show you a specific example now. What's on the screen there is a section to show just one level. Again, we're limiting the scope, showing only electrical and mechanical models. So again, we're reducing the total number of data sources that are coming onto the screen. And then we could automatically generate a report from here, just with these highlighted pieces, but it would have 126 items on it, even for what looks like a fairly simple area. And that's probably not very useful. So in order to communicate effectively with the people who will actually be resolving these issues, we sort the clashes into groups to report and resolve them. So I'm going to zoom into this area here just to give a specific example. A little closer, and then in 3D, there we go. So this is just that same view, but in an axonometric perspective. And what you're seeing is ducts in orange, and conduits in blue, and a junction box to the left there. And Everything that is not clashing is grayed out. But those models are still there. So you can see flex duct going to diffusers. You can see another junction box here, but those aren't part of this, this clash report. So the clash test in this small area shows 7 clashes. It shows 5 for the conduits, 1 for the junction box, and then 1 for the access panel under the junction box. And this isn't 7 problems to solve. And if we're talking about what actually needs to happen in order to make this an installable plan, this is just 2 problems. So for the junction box, we can create one issue by grouping access to the junction box and the junction box itself. And then for the conduits, we can group the other 5 issues. So a lot of what we do in our department is reporting and tracking those issues. And I hope that gives you a little bit more of a tangible example of what it does mean to clash test 2 models. And a big part of it is this interpretation stage where we're consolidating the issues into the minimum number of solutions that actually need to be identified. So that's the goal: put all the information in one place, make it easy to update and access, and then work with the expert in each discipline to iterate their models until it all becomes one cohesive whole. And that description doesn't mandate any particular software. No one owns the concept of sharing information. So we use lots of different tools to sort and process. And what's on the screen there is not everything that we use. This is just what was on my desktop. That folder called application shortcuts actually has a bunch more. And of browser-based platforms, I only have dedicated shortcuts for a few of them. So there's no one platform where VDC happens. It's a toolbox, it's a skill set, it's not any one piece of software. And part of what we do in the department as well is we evaluate the tools we have available. We test out other ones to see if there are upgrades or substitutions that we should be considering. For example, I wish there were an alternative to Revit with some backwards compatibility, so I didn't have to have these 5 different versions of it installed on my computer, which is painful. I want to walk you through some of these tools in particular, again, just to let you see through our eyes a little bit about how we're approaching these problems. This is what Navisworks looks like, and this is where that federated model, that infinite light table, is assembled for comparison and analysis. And this is a fairly typical Navisworks view. On the left, you're seeing properties, sets, groups, and a tree graph of everything that's contained in the model. And on the right, there's a reference plan view and a list of saved viewpoints. There are 2 versions of this platform. Manage is the one that we use for running clash testing, and that lets us save viewpoints and view styles and color schemes, run searches, organize the models. And then once we've done all of that, we publish that, and then anyone can view it in Navisworks Freedom. That's free. It's installed on Etro computers by default. And if your project has BIM resources available, Navisworks Freedom is probably the first point of entry for accessing them. All the models that I've shown up to this point were in a federated model from Navisworks. It is very much home base for a lot of BIM work. And I'm not going to go into this much detail for all of these tools, but this is an important one. And if it's not familiar to you, I hope that we can make it more familiar. So Navisworks is where we do issue identification. But to resolve issues, you do need to be able to communicate them and track them. And that's why there are platforms out there like Airtasks and Visto. Both of these platforms have a list of issues which connects to viewpoints in the model, so you can quickly communicate them, review them, and resolve them. They're both built around a model viewer, so when you go to a viewpoint, you get brought there in the 3D space. You can move the camera and the section planes to get more context for the issue. And in both of these platforms, each issue is its own little discussion page where everyone can add viewpoints, comments, informally request information, or if necessary, can escalate to an RFI or to another form of communication for things to be processed more formally. On the left, there's Airtasks. It's browser-based. It's very lightweight. It shares its design sensibilities and information philosophy with Airtable. So if you're already familiar with that, it will seem very familiar to you. And it's built for collaboration. It's very easy to share links and bring new people onto the platform. And on the right there is Revisto. It's more of the industry standard issue tracking platform for BIM. If project ownership is mandating and budgeting BIM on a project, this often ends up being their decision and their direction. It's pretty tried and tested, but it is expensive. Each user needs a separate license, which means that deciding whether you're going to add someone to your process is a decision rather than a given. And it does have somewhat intense learning curve in order to use it fully. So everyone using it needs to download a desktop version, learn how to use it. I would tend towards Revisto for issue tracking on huge projects with highly sophisticated and experienced trades, but Airtasks for just about every other case. And then here's another tool in our toolbox. This is CM Builder. It's a fairly new software by local company CAD makers. It has a huge built-in library of equipment and resources, and it's purpose-built for sequencing and logistics. Ivan and Antonio put together this particular scenario to develop steel installation sequences in tandem with the site logistics plan. And I'm going to fly through this video a little bit because it's too long for us to cover all of it. But I think it really speaks for itself in terms of how to understand how your site logistics plan is going to adapt to each new phase of a project. You know, being able to determine where you can position this mobile crane at every one of these project phases as the whole thing progresses is just not something that you can do all at once on one plan. And it's crucial for things like equipment sizing and equipment selection in general. So really powerful, and I wish that it got more use on more of our projects. This is a quantity takeoff platform. This is Assemble. The advantage of using a VDC platform for takeoff is you get an automatic visual check. If something is missing from your takeoff, you will see it missing from the model and vice versa. So this in particular is a Division 3 takeoff, and it's colored by category. So it's easy right out of the gate to separate your verticals, your slabs, your screeds, your foundations, whatever you need, whatever's important to you. And so, for example, on a structural steel project, it's very straightforward to use a platform like this to filter by the weights of the individual members to understand exactly where and when your biggest lifts will be. So this gives you access to not just quantity information, but quantity information that's flexible enough that you can get the information that you need out of it early on in a project. And then this slide and the next one are from Ivan's section of a presentation to BCIT practicum students. Thank you, Ivan. I'm not going to spend too much time on point clouds because they're kind of their own beast. But these views are from Recap, which is another Autodesk software. And what you're seeing on the left is real view of a project. So think of that like Google Street View or Matterport. This is a first-person walkthrough of the project taken from the scan that was done on the day. And then on the right is the point cloud data, which is not like a photograph. It's more like the output of a total station. Imagine if at each of these orbs, there are two data sets. There's 360-degree photography, and then there's also LiDAR. So it's as if you set up your total station at each orb and took hundreds of thousands of points. So that way, instead of listing everything you could possibly want to measure ahead of time and then going and measuring it specifically, you just go out and you measure everything all at once. And then you can extract the information you need from that a la carte. Obviously, that's incredibly useful for understanding site conditions, but it is a lot of data. Files like this are typically tens or hundreds of gigabytes. And so we use the specialty softwares like this, like Recap, for annotating and processing those data sets so that they can be used elsewhere. And one of those examples would be, this is Syn2. This is a platform that outsources the computing for that to their server so that anyone can view the point cloud in a browser, overlay models with it, and compare it to the design. And ideally, that means that everyone has access to it with a much lower barrier to entry right from the beginning. On the right there, what you see is in yellow, that's the duct layout according to the mechanical engineer's drawings. And in the best case scenario, your design engineer would have access to the point cloud and the existing conditions right from the beginning. They do have access to as-builts, but as we all know, they're usually incomplete and not the most reliable source of information. So ideally, this kind of thing would be factored into the design right from the beginning. But in cases when it's not, it makes it pretty obvious where you've got issues and gives you a pretty good case to make for getting that coordination done ahead of time. And then finally, this is Revit. This is what people often think of when they think of BIM. It's typically where new models are designed and updated. There are lots of specialty systems that do models for a specific system. There's AutoSprint for fire protection, there's Tekla for structural steel, but Revit is a bit of a jack of all trades. And this is an image directly from Autodesk's website, which looks great. They've got a little live render going on there. Lighting is turned on. It looks really gorgeous and presentable. When we work in Revit, it typically looks a lot less glamorous, but we're using it ultimately for a utilitarian endeavor. It's not really about the presentability of how it looks on the screen. And then here's an example of how we use multiple platforms to bring data together from multiple sources into a place where we can analyze it. So again, point clouds are too heavy to use in full on their own. But once you do know what you're looking for, you can narrow it down and you can bring in only the relevant points. Thank you to Excelsior Measuring and Dan for working with us to capture and process this data. In this project, the whole slab was poured by the base building contractors long before we mobilized to site. We didn't have continuous access to the whole area. And so coming in, we didn't know which slab penetrations had been cast into the slab and which ones would need to be scanned and cored. And the space here is a commercial kitchen space. So lots of MAPF systems do need to run in and out of those areas. So what you're seeing now is a slab plan that is the actual slab as built. Every pixel on that is basically a point from a total station. And where you don't see data, that's because the scan was blocked or there's no slab to scan. So those two large rectangular openings in the middle, that's real. Those really are openings. But then you can also see that there's white space inside the cores where it's blocked by walls. And those sort of blotchy areas with the rougher edges are puddles, which reflect lasers. So those areas don't show up in a laser scan. It's important to understand the limits of your technology. So we isolated only the points near the top of the slab. And I created new elements to add to the federated model so that everyone gets a better understanding of where the cans and the drains are that are already cast into the slab. And I've shown those locations with crosshairs here so that we can check the alignment with the equipment going in above. We can identify missing cores. So here are some right here. You might be able to see those two faint little circles. Those were the wish list of where we were hoping there would already be slab penetrations. And then from there, we can review what we know about the slab to analyze that area for how possible it'll be to core there. So on this drawing, this is the same slab plan. And now red is showing slab bands, which are full of rebar, and yellow is showing cast-in electrical duct banks, which I'm told you should not core through. In the next, here we are. In the area that I showed a moment ago, this is from that same spot in the green there. This looks like a pretty promising area to scan for new core locations. That there will be rebar and small conduits that we'll need to scan for and core around. But we can be confident that in a location like this, we will be able to find a location that will work. However, if we zoom in this red area up here, now those arrows are still showing up. It's not ideal. In those these little red sub areas, you can see that there's an electrical duct bank right underneath, and we're missing a lot of cores. So the time between me making this report and our site team getting enough access to this area to actually begin scanning and looking for new cores is going to be about 5 months. So in this case, well before we've got continuous access to the space, we can start weighing our options and mitigating the risk to the schedule that comes from having to get this area redesigned only in the moment once we're there to assess it up close. And finally, section 3, this will be the quickest one. We're going to just talk about how you can set your project up to get the most out of these tools. So first step for everything is to look at what you're trying to achieve. We saw with the pulsed curve, the first decisions you make are the most impactful. So as the GC, by the time we're awarded a project, lots of the project conventions are already in place. And documenting and expanding them to keep information flowing is crucial. So that's where a BIM execution plan comes in, and that should be reviewed early and often by all stakeholders, and that helps new trades come in. It's quite a technical endeavor, but I wish that I had 45 more minutes to go into just that. And then secondly, trade selection. And this is not something that is in my regular purview, so I'm not going to say too much about it. But first of all, sophisticated trades are already using these tools with or without us. Many projects are too complex for them to work any other way. So if we as the GC aren't there to support them, they won't be getting the full value of their technical investments. And then one more note on trade selection. It's not a set of decisions that can be made in isolation. If 4 of your 5 major subcontractors on a project are using BIM effectively, one of them isn't, it stops information from flowing freely, and it doesn't just slow them down, it slows everyone down. It's more than the difficulty of coordinating their system, it leaves everyone else in a position of uncertainty. So you can always cover gaps by outsourcing to third parties. The best case scenario, though, again, is always that the people coordinating the install are the same people who are working closely with their own site teams so that there's no discontinuity of information there. That's the final thing I'll say on trade selection. On budget, front-loading effort on a project can be a bit of a hard sell. Moving effort earlier also moves cost earlier. Etro does have the advantage already, though, of institutionally valuing pre-construction. We have a history of getting really great results that way. And so this value proposition is already familiar to us and to the partners in the industry that we work with regularly. I promised I'd come back to BXP. I'm going to do it very quickly. I wish I had time to go in more detail again. Essentially, we don't want to cause rework for the architects. They've already been working on a project for ages. We want to adapt what's already there so that as trades go on, we're minimizing the barrier to entry, getting the startup times shorter, and making onboarding as smooth as possible. And then the final line there is about LOD, which I also promised to return to. This is a typical LOD matrix. This shows who's going to do what, when they're going to do it, and to what level of detail. This is pretty dense. I want to just look at a couple of lines. This is just two specific examples. On the left there is the uniformat number, which is the definition that governs this level of development. And on the right is who is going to be the author in the model at any given point. So in the first example, we're looking at tower cranes, and this says WTW, temporary works, modeled by the GC. So early stages, we're taking on modeling responsibility for tower cranes with consultation from trades, of course. And then at IFT, this would transfer, in this case, to XTW, which is a temporary work subcontractor. And then on the bottom line here for fire protection, this is standpipes. Normally, these are considered by the architects from a very early stage in the project because they impact the space available for egress paths, and in turn, that has a big impact on the layout of the building's core in a typical concrete construction. So once there's a fire protection consultant engaged in a project, they'll take responsibility for the system, adapt it as necessary to meet the design requirements, and then finally, full IFT there, 350 XFP. That's when a fire protection contractor comes in, and now they're taking the fire protection design and creating their installation plan, their trade model. Obviously, the timeline, the contract structure, the requirements, they all vary pretty significantly between projects. So developing this matrix is a pretty crucial part of that early process. And now here's an illustration of what those LOD values mean. LOD 100, symbolic, usually is a 2D element brought into a 3D environment, so I haven't even shown it here. LOD 200 is when you first get into 3D and you have approximate size and shape. You know, equipment is generic. You might have a big square box that's just labeled transformer. LOD 300 is the right object in the right location. That means it's dimensionally correct. And you have the actual parts that you're intending to use. You have the actual equipment selection included. LOD 350, that includes interfaces with other elements like hangers, seismic bracers, and connection points to MEPF. So a model at LOD 350 is one that includes everything that anyone else could possibly need to coordinate their system with this model. And then LOD 400 is everything that you would need. This is something that you could send to your fabrication shop and they wouldn't have to ask any questions in order to actually produce it. Usually that's not necessary. If too many systems are modeled at LOD 400, it becomes much more expensive to change after the fact, and it often also bloats the data. So this is information that's usually not required for broad coordination. And then LOD 500 is exactly as detailed as LOD 400, but after the system is installed, you go back, you measure, and the model gets updated to precisely match the reality. So managing LOD progression is really crucial, and this needs to happen in sync throughout the project. There are some common pitfalls that affect lots of projects, which are things like overpromising, and that's a problem even if they do deliver to the promised level. If someone is requesting or offering LOD 400 information, and you're 6 months away from having an IFC design, you need to ask yourself how that information gap is going to be filled and whether those necessary assumptions will hold up as the project progresses. And then secondly, an issue that gets run into a lot is clash testing before the prerequisite LOD is available. So there are some aspects of coordination that can't be done before a prerequisite level of development. In Vancouver, it's unusual for framing trades to be involved in BIM. So if you're looking for issues with header beams or stud packs, that information just won't be available until you get shop drawings, at which point someone would still have to update the architectural model to include that information in the BIM. And what that means is that there are types of clashes that can't automatically be detected. And even if they are, it'll come much later in the process. So if that kind of coordination is important for managing risks on your project, it's important to consider how that will be accounted for, how that data will get into the environment where you can use it. I'm going to wrap up in just a moment. Sorry to go over time here. But before I do, I just want to revisit this graph one more time and give you a bit more of the motivation behind this in the first place, just to remind you where we started. The later you go in a project or a project phase or any task, the more expensive it is to make changes. Coordination is misalignment of information. And the way to rectify misalignment of information is change. So the earlier you can find the misaligned information, the earlier you can make the change to align it, and the more impact that has on the success of your project overall. So the crucial takeaways, final slide. Remember that Paulson curve. There are a lot of aphorisms for the same concept, aphorisms. And it's because it's important in a lot of context. You've heard an ounce of prevention is worth a pound of cure. A stitch in time saves 9. This is the fundamental reason that we look for these tools and that we do this. Secondly, understand your goals, choose the right tools to achieve them, and then allocate your time and effort efficiently to get the most out of them. None of this works in a vacuum. Communication is fundamental to every step of this. Your biggest barriers to project success are discontinuities of information. And that means getting buy-in to the process from the beginning and keeping communication channels as open as possible throughout the whole project. And then most importantly, keep the central priority of the process in mind. We're trying to identify misaligned information sooner so that we can align it early while the cost of change is still low. Coordinated models are a heuristic for success, but they're not the whole objective themselves. It's the process of creating and coordinating them that brings the project into focus and lets everyone align their understanding. So the goal of our department is to get everyone on exactly the same page about what we're building and how we're building it. I hope today I was able to give you some context that will help you to help us to help you to achieve that. And here's some quick reading links that you may or may not dig into. This first one is a PhD thesis, which I highly recommend. And then the second two are a little bit more technical, but we'll have just about every answer you could possibly be looking for. I'll turn it back to Karina. Thank you very much.
Thanks, James. That was a really excellent presentation.